has been defined in R. Okay, if to each point x, y, z of a region R in space, there exists a number of scalar phi of x, y, z, then phi is called a scalar function. Full stop. And we say, we can write them together, and we say that a scalar field phi has been defined in R. Okay? So, listen. So, this simply means that so we have a function, listen now. If you have a function that depends on x, y, z, and it is not in vector form. For instance, look at this now. If I have something like this, if I have f of x, y, z to be something like x, y, z. Okay? This is a function of x, y, z. I can call it a scalar function. Why? Because it takes in inputs x, y, z and it produces a number, which is a scalar. Does that make sense to you at all? It would be different if I had something like this. Maybe I have something like a of x, y, z is equal to xi plus xy j. You understand what I'm doing? Plus x cubed k. Okay, this would be a vector function because it takes in the input x, y, z and produces a vector. You understand this idea now? So that's what I mean by a scalar function. So, and its region, So, in its region of definition, we say that we have a scalar field here. Okay? In this situation also, the region of definition, we say that we have a vector field here. Does it make sense to you? So when I say scalar function, vector function, that is what the symbol is. It means that when I put in my numbers for x, y, and z, I'm going to get a scalar at the end of the day. That is just a number. And in the case of the vector function, I'm going to get the vector, which will be in terms of the unit vectors I, j, k. Does that make sense to you at all? So that's just the difference between them. It's something quite easy. So let's move on, please. Let's move on. Examples of scalar fields. Examples of scalar fields are examples of scalar fields. Examples of scalar fields. Number one, the temperature at any point. The temperature at any point. The temperature at any point within or on the Earth's surface. Within or on the Earth's surface at a certain time, defines a scalar field. The temperature at any point within or on the Earth's surface at a certain time defines a scalar field. Why? Because the temperature also varies with position. At different positions, we have different temperatures. Does that make sense to you as well? And that temperature is a scalar quantity. Abi? So if you define temperature by position, definitely you are going to have a scalar field. Do you understand what I'm saying? Okay, so that's that about that. Another example, number 2, you can write this as the next example. F of x, y, z is equal to x, y, z. Is that clear? F of x, y, z. That is another example of a scalar field. Right. So when you come across these things, just know what they mean. Of course, in most cases you will come across, you don't see maybe someone has actually randomly defined some function for you to analyze. Okay, but in reality, you actually have applications in reality. Okay? That example of this one we just talked about. So if you want to analyze temperature variation on the Earth's surface, for instance, then you have to define some scalar function. Okay, so let's move on. So we talk about vector field. The vector field. If to each point x, y, z of a region R in space, there exists a vector v of x, y, z. Then v is called a vector function, and we say that a vector field v has been defined in R. And we say that I said scalar?
1 million times.
And we say that the vector field V has been defined in R. Sorry. Alright. Examples. So I give you an example. So example, write it down. Number 1. If the velocity at any point within a moving fluid is known. If the velocity at any point within a moving fluid is known, at a certain time, comma, then a vector field is defined. So if I want to study the velocity at different points in a moving fluid, okay, and I know how the velocity varies with position, then with that I can define a velocity field. Does that make sense to you at all? That means I will define a velocity function that will be in terms of x, y, z, or whatever the coordinates of position are. Do you understand what I'm saying? Okay. That is an example. I said, if the velocity at any point within a moving fluid is known at a certain time, comma, then a vector field is defined. That means the velocity at any point, that means the velocity variation with points, okay, actually forms a vector field. Do you understand what I'm saying as well? Okay, for instance, this could be the situation. For instance, if I have something like this could be representing velocity at different points in the field. So I'll just find out, I want to get the velocity at the point, I'll just find out what is the x coordinate at that point, what's the y coordinate at that point, and I'll slow them in here. I'm going to get a velocity, which is a vector at the end of the day. Does that make sense to you? That's what we mean by a vector function. And that constitutes a vector field. So that is that about that. So let's move on, please. Let's move on to other things. I've told you we have not started the course yet, and I don't think we will start it today. We're just looking at things we have done before. So some of these things will look very, very familiar. The things we've done before in MTH 104. So just to refresh our memory, and for those who did not do MTH 104, so that you can relate with the things we will be doing in this course. That's what we're going to do all of this. Alright, so let's talk about dots and cross products of vectors. Dots and cross products of vectors. Dots and cross products. Alright, right now, dot products. Dot product is also known as scalar product. The dot or scalar product of two vectors A and B. The dot or scalar product of two vectors A and B is denoted by A dot B. Denoted by A dot B. Okay, is defined as A dot B is equal to AB cos theta. The dot or scalar product of two vectors A and B, denoted by A dot B, is defined as A dot B. Defined by A dot B equal to AB cos theta. Do you get that? AB cos theta. I told you earlier, when you see A standing below that way, it means the magnitude of A, Abi. B standing below that way, it means the magnitude of B. So, and theta in this case is the angle where theta, right now, where theta is the angle between the vectors A and B. Where theta is the angle between vectors A and B. Where theta is the angle between vectors A and B. So, you know why this is called scalar product or dot product? Because the result is a scalar. Obviously, this result is a scalar. We are not multiplying, we are not adding any unit vector to this to describe that. But this is actually a scalar. So when you take a scalar or dot product of two vectors, you are going to be getting a scalar. It means you are going to get an ordinary number. Do you understand what I'm saying? Real number. Right? So that's about that for the scalar product. So the following are, listen now, so the following are some laws. Okay? If you want to do, you can say algebra of dot product. Equal to B dot A. A dot B is equal to B dot A. Obviously, you can interchange them. Interchange this. A dot B B dot A will be VA cos theta. VA is the same thing as AB. You get that? So basically they are the same. And we have A dot B plus C equal to A dot B plus A dot C. That is, it is distributive over addition. Dot product operation is distributive over addition. We also say that M, of course, like we defined earlier, the first algebra I gave you, M still has the same meaning here in the scalar. You understand what I'm saying? I gave you this earlier. A, B, C are vectors, M and N are scalars. When you come across them here. So this is going to be M into A dot B. The same thing as M A dot B. M A dot B, which is the same thing as A dot M B, which is the same thing as A dot B multiplying M. So, I hope you get this. It means that this now, you can simply treat this as multiplication. You are multiplying these two. You are carrying out dot product operation, and you have a scalar outside, just some number outside. This simply means that you can multiply either of them first by M and then carry out the operation, or you carry out the operation and multiply your result by M. Which doesn't make any difference. The next one, number 4. This is for unit vectors I, J, K. I dot I is equal to J dot J is equal to K dot K, and it is equal to 1. That's if we are taking I dot I, J dot J, K dot K, where these are the unit vectors in the X, Y, and Z directions, this is going to give you 1. And that is, if they are the same, you're going to get 1 as your result. And if they are different, you're going to get 0. That's I dot J, J is equal to I dot K is equal to J dot K, and one of them is going to give you 0. Is that clear? When they are different, you're going to get 0. Is it clear? Okay, so that's bad about that. And we also say that now if you have these vectors written in component form, if I have vector A written in component form as A is equal to, if A is written as A1I plus plus A2J plus A3K, and B is also written in that form as B is equal to B1I plus B2J plus B3K. Then for the dot product, you can write these as follows. That is, we know them in magnitude form. Of course, if you know the magnitude of A and magnitude of B, and then the angle between them, or we desire the angle between them, you can do this. It's fine. If you have them in components form this way, and you want to get the dot product, of course, to be a longer journey to begin to find their magnitude and the angle between them first. You understand what I'm saying? So it's better you use this component directly. So that's what we're writing this out. I know for some of you this looks like an insult. I'm teaching you how to do dot product in 2021. So I'm sorry about that. So A dot P is going to be equal to A1 B1 plus A2 B2 plus A3 B3. So it simply means that we multiply their respective components. Multiply X component by X component plus Y component by Y component. Do you understand that? Plus Z component by Z component. So, and then you want to get A dot A, for instance, we need A dot A. You know that is going to be A1, Abi. Do you get that? Plus A2, A2. That's going to be A1 squared plus A2 squared plus A3 squared. Does that make sense to you? And similarly, if you want to get B dot B, B dot B can be written as this. Can write this as B dot B equal to B1 squared plus That's all about that. Okay. So look at this now. And finally, we say that if you have two vectors, A and B, and if A plus B gives you 0, okay, there are some conditions that may be responsible for this. Listen to this. If A dot B gives you 0, it could be that A is a 0 vector, B is a 0 vector, or both of them are 0 vectors. And when that is not the case, it means that the two vectors are perpendicular. So the two vectors are perpendicular. So they're going to have this to be 90 degrees, Abi? And cos 90 is going to give you 0. Does that make sense here? Right. So if A dot B equals 0 and A and B are not null vectors. You understand what we mean by null vectors? That's 0 vectors. You get that? They are not 0 vectors. Then A and B are perpendicular. Let's say 3 mutually perpendicular vectors or unit vectors. You can call them orthogonal vectors, meaning that they are mutually perpendicular. That means for any pair you pick, the two elements here, the two vectors are very perpendicular. Right, so and this is the way you can verify. Now I want to verify that two vectors are perpendicular. That means I can try out the dot product and see whether or not it gives me 0. If the dot product gives me 0, definitely the two vectors are perpendicular. Does that make sense? Right, so that's that about that. Let's move on. So let's talk about the cross products. The cross or vector product. So say this one was dot or scalar product. So we'll talk about cross or vector product. Cross or vector product. The cross or vector product. Cross or vector product. Right now. The cross or vector product. The cross or vector product of A and B. That's vectors A and B. The cross of vector product of A and B. That's vectors A and B. Is a vector C. Is a vector C defined by C equal to A plus B, which is equal to AB sine theta U. AB sine theta U. The cross or vector product of vectors A and B is a vector C defined by C equal to A cross equal to AB sine theta. Listen very well. You know why we're putting this? You know the implication of this, right? This is to tell you that this is a vector, Abi. And how do I express the vector? The magnitude of the vector multiplied by the unit vector in its direction. Abi, we have seen that earlier. If I want to write any vector, I can express it as its magnitude multiplied by the unit vector in its direction. Is it clear? That's a good representation. So this is recognizing the fact that the cross product of A and B is not a scalar, it is actually a vector. Its magnitude is AB sine theta, and U cap here is to represent its direction, or the unit vector in its direction. Does that make sense here? So, how do you get the unit vector in the direction? Listen now. So this is, listen, so the direction of this is a direction perpendicular to the plane containing vectors A and B. Okay, the direction is a direction perpendicular to the plane containing vectors A and B. So you can write now. You can write this. Let's write this down. The direction of C. The direction of C. The direction of C is perpendicular to the plane. It's perpendicular to the plane containing A and B. Containing A and B. Containing A and B, such that A, B, and C, such that A, B, and C form a right-handed system. Such that A, B, and C form a right-handed system. Jerry, how far now? I'm just Yeah, no worry, you go so full, you go go back your style again. That's like Manuel. Alright, so before we write down the system, so we've done this illustration before. If you have two vectors A and B, listen, look at this. You have two vectors A and B. This is vector A. You probably would not need to use this here, but it's good to know it. We have two vectors A and B, and you take their cross product. Let's say you take cross product of A, let's say A cross B. Here, the order is important. Unlike this, where the order is of no importance, whether you take A does B or B does A, you're going to get the same result. But here, that is not so. And you're taking A does B. So imagine that you want to cross A into B. That is, you want to make A align with B. So I gave you this illustration before. Imagine that you have a right-handed screw. Yeah, the common screwdrivers you are familiar with. Right-handed. So look at this now. You want to rotate this. You want to rotate this vector so that it aligns with this. How do you have to drive this? You have to drive it this way. When you drive it this way, what will it go? Is it inside or outside? Inside. That means the direction of the cross product is going to be inside. Perpendicular to the plane, which is this board, and it's going to be right inside. Does that make sense here? The perpendicular to the plane will be inside or outside. Does it make sense? Right. That's how to get the. That's what we mean by the direction is perpendicular to the plane containing the two vectors. In this case, this board is the plane containing the two vectors. So the cross product is going to be in the direction perpendicular to the plane. So either outside this way or inside. You understand what I'm doing? So that's about that. That's the way to get this direction. Right. So that is that. So let's move on, please. So the laws that we apply here, the laws of cross products, something similar to how we wrote out on laws for each dot product. So let's write something similar for cross products. Please don't joke with all these things. Especially shows I'm missing out. They are the most important part of the things we are doing here. Please, all of them. All these A dot B is equal to B dot A. Please know them very well. So we have this for cross products now. The first one is that A cross B is not equal to B cross A. It is rather equal to minus of B cross A. You get that? And number 2. A cross B plus C equals to A cross B plus A cross C. That means it is distributive over addition. Just like the dot product is distributive over addition. We have M, that is M is a scalar, like we said earlier. Please keep quiet, please. So if I multiply the cross product by a scalar, I can decide to multiply any one of them by the scalar first, or get the cross product and multiply the result by the scalar. So this is going to be, just like we have this for the dot product, then we have something similar here. Why is not showing that my Yeah, when you have them to be the same, you're going to get 0. How do you know the difference between, listen please, there's no the difference between 0 with arrowhead and just 0. You know the difference, right? The one with arrowhead is 0 vector. The one without arrowhead is 0 scalar. That's the 0 you are used to. Please note this difference. You can be given an OBJ question where the saving grace will be your ability to recognize which one is 0 scalar and which one is 0 vector. Did you get what I just said? You can be given OBJ question. Math department can give you OBJ question where the saving grace will be your ability to identify what should be 0 scalar and what should be 0 vector. Please note the difference. Any cross product operation must result in a vector. Does that make sense to you? Any cross product operation must result in a vector. Any scalar product operation must result in a scalar. Does it make sense to you? That was why when we wrote I dot j the other time, we wrote out the answer as 0. Simply 0. There was no bar on it. It's not the difference. Okay, so for this, you have, when they are different, for instance, when you have I plus j, equal to k cross j, equal to k, and then j cross k equal to I, and then k cross I equal to j. So how you know that is if you please listen now, if you arrange them in this order, you arrange them in the order I, J, K. And so far you are going this way, you are going in this direction. Please pay attention. So far you are going in this direction and taking the cross product, you get the positive results. You know what I'm saying? So I cross J is equal to K. K cross I is equal to J. Do you understand that? J cross K is equal to I. But if you are going in the opposite direction, you get negative. Do you understand that? So this is going to give you the next one. That's not about number 4. Number 5. If A, in this case, now you have them in component form that we considered earlier. If A is equal to A1I plus A2J plus A3K, and B is equal to B1I plus B2J plus B3K. Then A cross B is equal to, this is best found using the determinants approach. You get the determinant of I, J, K. Note that order is of importance, so I have to keep to the order. A comes first before B. So I'm going to put A1, A2, A3, and B1, B2, B3. Does that make sense? If you can remember the properties of determinants, you see that when you interchange a row or column of a determinant, you are going to multiply the determinant by -1. Does that make sense to you at all? Okay? That's why if I move this up, if I interchange row 2 and row 3, for instance, I'm going to have a negative of what I have here, which confirms that A cross B is equal to minus B cross A. You understand what I just said? So that's about that. Alright, so let's move on. Number 6. The magnitude of A cross B, the magnitude of A cross B, is the same as the area of a parallelogram. The area of a parallelogram with sides A and B. If A cross B equals 0, this is 0 vector. If A cross B equals 0, and A and B are not null vectors, and A and B are not null vectors, that is, they are not zero vectors, what do you expect to happen? Yeah, so if they are not null vectors, that means the angle between them is zero. That means they are parallel vectors, or say collinear vectors. So then we say that then A and B are parallel. Then A and B are parallel. Alright. So that's that. So what do you mean by saying two vectors are collinear? Please listen now. Collinear simply means that they lie on the same straight line. Look at something. You can have, earlier I talked about the fact that you can have some vector, and the unit vector in the other direction as I, and then you have another vector, let's say the other vector is 2I. It's also going to lie along the same direction. If you have another vector, say the vector is of magnitude 5I, it's also going to lie in the same direction. Do you understand what I'm saying at all? So if they lie along the same line, we say that they are collinear. Basically, they are collinear because I can write one as a multiple of the other. So if I have two vectors A and B to be collinear, it means I can write A to be equal to KB, where K is some constant. Do you understand what I'm saying at all? So whenever this is possible, we say that the two vectors are collinear. K is just some real number, whatever the real number might be. So when you have two collinear vectors as well, definitely the angle between them is going to be 0. There's no angle between them basically. So you're going to have this something to be that. And if you have the two vectors to be oppositely directed as well, that means you're going to have the angle between them to be 180. If sine of 180 is still 0, so you're still going to have that same idea. Do you understand what I'm saying? Alright, so that is, if you have two vectors to be parallel or antiparallel, antiparallel means they are oppositely directed. Okay? You're going to have their cross products to be. That's about that. So let's talk about triple products. Triple products. Like I said, I know some of you will find this result, but don't please. If A is equal to this and B equal to this, find A cross B. Somebody work on it. You got something different? Minus 10. This last one. What did you get? Alright, so we can take the product of three vectors in these three ways. Look at this now. You can have something like this. Please pay attention, pay attention. So just know that the dot product and the vector product that we talked about, the dot product and the cross product that we talked about, can only be applied to two vectors. So just have that in mind. So it means that I can do something like this. A dot B cross C. So B cross C, why can I do that? B cross C is a vector, A is a vector. So I can take their dot product. Does it make sense to you? I can also do something like A cross B cross C. Why can I do this? This is a vector and this is a vector. Does that make sense to you? Okay. I can also have something like this. A dot B multiplying C. Does this make sense to you? A dot B is a scalar. So basically, I'm multiplying vector C by a scalar. Is it clear? So all these are reasonable operations that I can carry out on the vectors A, B, and C. Does it make sense to you? You get it? So you can get each one of them. So use the vectors just given to you now, and C equal to plus K. So carry out each one of them and tell me your results. This third one simply means I'm taking, no, there's no operator here. I'm taking A dot B, which will give me a scalar, then I'm using to multiply this vector. Does it make sense? So that's going to be a scalar multiple of the vector C. Is it clear? Alright, to carry out all these operations one after the other, using the vectors A and B defined earlier, and this vector C. Oh yeah. So you can easily get this. Insofar the order is not changed. Please pay attention now. You know this is A, B, C. Okay? You can get the same thing by starting at this point again. Do you understand that? So far the order is reserved. You start at this point or any other point. So this is this. You have B, C, A. Just like you have A, then coming back here, B, C. Is it clear? You have A, B, coming back here, you have C. Hey, does that make sense to you? No. Okay, not like this. We have A, B, C. You are going this way. You can pick any of them along that path. That means I can do A dot B cross C. It's the same thing as C dot A cross B. Big here. The same thing as B dot C cross A. Does it make sense? So far you are going that way, you get the same result. And number 3, because basically they are all equal to this. When you do their, when you carry out this operation, you can do it with determinants. The same thing as having A1, A2, A3, B1, B2, B3, C1, C2, C3. So this is just like I'm multiplying B cross C. If I want to do B cross C normally, I will have I, J, K, K. Do you understand that? But instead of having I, J, K, I'm having the components of A. So give me this two products. Number 3. A cross B cross C is not equal to A cross B cross C. Number 4. A cross B cross C is same thing as A dot C divided by B minus A dot B multiplied by so you can simplify this. If you want to do this vector triple product, you can take it as, please pay attention, having B out here first and also having C out here second, and then you follow the same order. A will come first, A will come first. Of course, it will not matter here because A dot C is the same as C dot A, and also A dot B is the same as B dot A. But you can simplify the vector triple product that way. Does it make sense to you? So, you will see some application of this during this course. We will apply it at this point. You just know what it is for now. And you can verify or test it also with those examples I gave you earlier, vectors A, B, C that I gave you earlier. And we've done something like this in MTH 104. You can still remember. You still have your. I've forgotten it. Vector differentiation. So these are all separate topics in MTH 104. We are trying to summarize. Okay? Because they are very, very valuable. Yes. Vector differentiation. The MTH 104. Now you remember. So vector, listen now, listen. So vector differentiation is done, discipline is done the same way you do a normal differentiation of functions. The differentiation method you already know, you apply. Listen, please, listen. So the only difference is that, listen please, the only difference is that you have to preserve order of vector products. That's what I'm saying at all. When you have vector products, you have to preserve their order. If you have, please listen now, if you have A cross B, for instance, let's say this is a vector function, A is a vector function, and B is a vector function, and we have A cross B. I know this is a vector, and I want to take the derivative of this. Let's say we represent some variable t. I want to take the derivative of this. Yeah, I will do it the usual way. I will do normal differentiation, where I have to use the product rule. Take one as a constant, differentiate the other, plus take the other as constant, differentiate the first one. Does that make sense to you? The only difference is that here, I have to preserve their order. That means the one that comes first has to remain first all through. Is it clear? So if I want to do this now, this is going to be something like the A. See, I'm differentiating this one. I'm keeping this one constant. Cross B, plus I'm differentiating B and keep A constant. But I have to maintain the order. So it will be A cross D, B, C. Does it make sense? That's the only thing you have to bear in mind. That the order has to be preserved. So that's that. That's that about that. So let's look at some rules. Or some implications of these rules. Okay? These are this differentiation formula. So you can write now. Differentiation formulas for vectors. V, U. U is some variables in terms of which these functions have been defined. Let's listen now. So we have functions A, B, C that we use here as scalar functions. So you can write now. So in the following rules, A, B, C are scalar functions. It has been defined in terms of variable U, and phi is a vector. A, B, C are vector functions, and phi is a scalar function. So with that, you can write the following rules: derivative of A plus B, derivative of A plus B with respect to U is going to be equal to. So this is addition. Okay, this one does not matter. Even though we write it in order, it doesn't mean it has to be in order. You understand what I'm saying at all? Addition is still commutative as before. So this is just going to be equal to the A, the U, plus the B, the U. And the next one, derivative with respect to U of A dot B. Hello, listen. We said something earlier that. Hello, listen. We said something earlier. When we started, we said that A dot B is equal to B dot A. It's not a blanket rule. There are some cases where they are not equal. All I do is some operators it will not be equal. You get to see in this course. So when you are doing, see anything that involves vectors like this, just preserve the order and be safe. Do you understand what I'm saying? If it doesn't matter, you are safe. If it matters, you are still safe. Do you understand what I'm saying? You just need to preserve the order. So this is going to be like this: the A, the U, dot the B, dot B, plus A. So I'm differentiating this while using this constant. That will be A dot the B, the U. Look at this expression. Phi is some scalar function, A is some vector function. So we're still going to apply our rule. We're still going to apply our rules of differentiation. No, this is not a scalar constant. If it was a scalar constant, of course, we'll just move it out of the differentiation sign. So this is going to be equal to phi. Okay, I'm keeping this as constant. I want to differentiate this. Phi A du. Du. Thank you.
You don't have to
Divide du A. Alright. Just trying to preserve order. That is why I was doing it that way. This is going to be du of A dot B cross. So here we have three vectors. So we're going to apply our product rule. So we differentiate them in terms. We pick one, differentiate it, keep the others constant. Pick the next one, differentiate, keep others constant until we get through everything. So I'm going to pick the first one. A du dot B cross C. You understand that? Plus differentiating this, keeping others constant. A dot dB du cross C plus differentiating this, keep A and B constant. That's going to be A dot B cross the C du. You get it? That's good. Yeah. Yeah. What is it? Just matter. This one? Which one is this one? Hey, now sure, it doesn't matter. Preserving order means this one means by preserving order. A is coming first before B. Not really differentiated, not necessarily differentiated first. You get that? Whether this was here or here, what matters is this product, this vector product, other vector product. Sorry, I'm in the over there. Why? Next. Which you can expand, you know, it's going to be like, then you can expand this. over that expression. So when you do that, you're going to get something like this. A dot then y dot down x plus then a then x down b then y down square. That's what you get. Alright, so finally, differentials of vectors. Differentials of vectors. How do you know the difference? Differentials of vectors. Non-differential differentials of vectors. Other than you can write this. Okay, this one. So you can expand this. Listen out. You know this means derivative, second derivative, differential with respect to x first, then with respect to y. So I can write this outside. Differentiate with respect to x first, what I have here. So this thing here is the same thing as having del y of this derivative is what we have written out in results. Does it make sense? So I can put in what I have here into this. That is going to be a dot del b del x plus del a del x dot. Is it making sense? Does that make sense? Then I can differentiate that with respect to y. Is it clear? I'll pick this first and differentiate with respect to y. Differentiate with respect to y, you have to preserve the other. So I can keep a constant. I differentiate this one with respect to y. That's going to give me this. Is it clear? Plus differentiate a and keep this constant. So that will give me this. Does it make sense? Then do the same thing for the second one. To give you this. You get it? Yeah. So let's move on. Differentials of vectors. Differentials of vectors. If a vector function is equal to a1i plus a2b plus a3b, then the a from our knowledge of MTH 201. A is the same thing as the A1, I, but it's also going to be a vector. So what we're simply saying is that differential of it is equal to the differential of its components. You get that? So we give you the differential of its components and put all of them together. A2A plus the A3K. It's going to be a vector given by that. I'll not get the differential of each of its components and put all of my results together. So, and similarly, I want to get the differential, for instance, of a dot it is going to be given by a dot differential of b plus differential of a dot b. So I have it as cross product. Differential of a cross b, same thing as a cross differential of b plus differential of a cross b. Finally, if a is equal to some function of x, y, z, then equal to del a, del x, the x, plus then then y dy plus then a del c. Since you have it that way, you can take the derivative and to give you the total differential. Of course, this does not contradict this. I hope you know the actually thing is here. Look at something. For instance, if you have, pay attention now, pay attention. Let's say for illustration, if you have a vector function, let's say we have something like xy I plus 2y squared j plus 3qk. This is a vector function. If you want to get its total differential, you're going to have if you want to get the a, it's going to be equal to derivative, partial derivative of this with respect to x, so I can differentiate partially with respect to x. What would that give me? That's going to give me y, abi? That's going to be y I. I'll differentiate partially with respect to x here. That's going to give me 0, abi? Yeah. There's no other one, there's no other one here. That is all I have, and then dx. Is it making sense? Plus differentiate partially with respect to y. I'm going to have xi plus this is 4yz. 4yz then with respect to y, it's not there, happy? Yeah. Then dy plus differentiate partially with respect to z. This is 0, this is going to be 2y squared j. So I have 2y squared j plus 3z squared k dz. Okay, so this is what this equation is expressing. It is okay this way. And I can actually recognize that this differential is actually a vector. And so I can write it in vector form. In that I will bring the like coefficients in terms of the unit vectors together. Does it make sense to you? So I can express this as those containing I, picking them together. I'm going to have y dx plus x dy I. Does that make sense to you? Did you get that? That's what this equation is expressing. I can have the a1 I. Is it clear? The a2j. So I can bring those components together. I can write this as plus a2. That those that have j. These are the two that have j here. That is going to be 4yz dy plus 2y squared dz multiplied by j. Is it making sense? Then those that contain k, that's the only one here. That's going to be plus 3z squared k. Is it clear? K. So these are the components of the differential. So that's very Is it clear? We're just collecting items. Those that carry I, put them together. These are the ones that carry I. Right here. I have to write this in vector form in terms of the components I, j, k. So those that carry I, I'll put them together. This is y dx together. Y dx I. So I'm putting y dx here. This is x dy. I'm putting it here. Then everything is I. Do you understand that? Line I. And I have those containing j. I have this and this. Bring them together. This is 4yz dy. This is the 4yz dy. This is 2y squared dz. So I put that also. 2yz dz. Then multiply by j. Does it make sense? Then I will write the last one. The one containing k is 3z squared dz. Is it making sense? Yes. So these are the two forms of it. So they are not contradictory. You can have it in this form where the x, the y, the z are the coefficients. You can also have it in vector form where I, j, k are the coefficients. That's what we main express here. So that is not about that. So we have a very good background now. So let me give you some assignment to work on so that you can master this properly before we meet in the next class. So we are not with the background, so we don't start with on Thursday. If phi of x, y, z is equal to x, y squared z, and a vector function is given by xci minus x, y squared j plus y, z squared k. Okay, if this is equal to this and this is equal to this, find del q then x squared C of phi A. Number 2. Number 2. Please listen now. If blah blah is equal to I del del x plus j del del y plus k del del c. Wait. This is a vector. Apply another vector. I have it as coefficient of. Alright, ladies and gentlemen, let me perform in that set of today's class. I'll see you on Thursday. Those of you who are in to see tomorrow morning.